In the previous videos, we introduced hashing. We talked about its applications. Let us now begin the concept of hashing. Before we talk about concepts of hashing, we need to understand this concept, direct address table. The whole idea of hashing is based on this simple concept. To understand direct address table, let us consider this problem. We have 1000 keys and values of these keys are from range 0 to 999. We want to efficiently perform these operations: search, insert and delete. So here are some example operations. If I insert 10, then I insert 20, then I insert 119, and if I say search 10, my output would be true. 10 is present in the table. Then I'll search 20, output will be true because 20 is also present. If I search for anything which is not these three, then output should be false. Then I delete 119, and then if I search for 119, the output is going to be false because 119 has been deleted. So we want to perform these three operations on the keys which are having range from 0 to 999. Please pause this video and try to think of a solution that can perform search, insert and delete in big O of one time. This does not require knowledge of hashing. You can solve it by using some of the basic data structures that you studied so far. I think most of you must have guessed. The idea is simple. We create a Boolean array of size 1000. We initialize this Boolean array all values as 0, 0, 0. Right? So here is an array of size 1000. Indexes are from 0 to 999. All the values are 0. So all these values which I have skipped here using dot dot dot, they are also 0. All the values are 0. Right. Now when I say insert 10, what I do is I go to this index 10 and change it from 0 to 1. When I say insert 20, I go here and insert here, make it 1. Insert 119, make it 1. Now when I say search 10, I just need to go to this index 10 and find the value of it. If it is 1, then I'll say that element is present. Otherwise, I'll say element is not present. Search 20, I'll go to it in this index and find if the element is present. If the value is 0 or 1, value is 1, so I'll say element is present. Since arrays have random access, all these operations, insert and search, are big O of 1. You can go to particular index and big O of one time. Delete 119. So what I'll do, I'll go there and make it 0. Basically, I'll do this operation. Table 119 is equal to 0. Right, that's what I'll do in the delete. If I write about general index, that's my delete operation. Delete I will do this. Search I will return whatever is the value of table I. If it is 0, then it will return 0. If it is 1, then it will return 1. Insert I will simply do this, where I is a key to be inserted. Table I is equal to 1. So all these are simple operations. They are big O of 1 operations, and we are able to achieve all these three operations in big O of one time. Big O of 1 in the worst case. Even if your keys are not from 0 to 999, they are in a range. For example, they are in a range from 1000 to 2000. Or 1000 to 1999 for simplicity. Right. Even if they are in range 1000 to 1999, what I can do, I can still implement these operations. What I'll do in this case, I'll subtract 1000 from all the values. That's how I'll be able to figure out whether the key is present or not. So if I am inserting 1010, that will be same operation as inserting 10 in the previous example. So this direct index table, it handles search, insert, delete when your keys are small, from 0 to 999 or some other smaller value, which can be created. An array of that size can be created in memory, and we can do all these operations in big O of one time. Not only this, it is able to handle small range values like 1000 to 999. A good example is ASCII values. For example, if you want to insert all the alphabet characters, small a to small z, you can use an array of size 26. These values start from 97. Small a is having ASCII value 97. You can subtract the ASCII value of small a and do all these operations in big O of one time with using an array of size 26 only. So this is direct address table. We have a data structure that provides search, insert, delete in big O of one time for certain input. Now, what are the problems with this direct address table? Why do we need another data structure like hashing? The problems with this data structure are it cannot handle large values. For example, if phone numbers are keys, phone numbers are 10-digit numbers. If you want to use phone numbers as an index in an array, your array size is going to be 10 raised to the power 10. So one problem is large keys. Another problem is floating point numbers. For example, 10.137. You cannot use these numbers as an index in the array. Third problem, your keys can be strings or they can be addresses. If your keys are strings, for example, geese for geese are string, how will you use this as an index? So these are the problems with this direct index table. It does not handle large values. It does not handle floating point numbers, does not handle strings or addresses or any other thing which is a combination of digits and characters. That is where the idea of hashing comes in. We'll talk about the idea of hashing in the next video.